if you've done a Google search recently, and I know you have probably noticed that there is now an AI overview at the top of every query. So it turns out that including that AI overview costs 10 to 30 times more energy than without it. So every time you're making a Google search now, it's calling a model and creating that extra cost in electricity. And that is going to have a huge impact on what electricity looks like across not just the US, but the world. So I'm worried about that. I don't know if you all are. But my research is trying to address this by trying to build computer hardware that is inspired by biological brains that can be more energy efficient. Now, when we're building this hardware, we're not just looking at building the structure of the computer to be more inspired by the brain, but we're also trying to be more inspired by how the brain actually operates. So my field is a field called neuromorphic computing. If you remember your high school Latin, that's brain-shaped computing. So we are, it's super on the nose. We are trying to build these new types of computers that take that inspiration from the way the brain operates to try to get more energy efficiency in running these sort of AI-style operations. So what makes them different from traditional computers? In the hardware, we implement neurons and synapses. They operate in a massively parallel way. They communicate with spikes, and the different components within the hardware operate in an event-driven way. They only do work when there's work to be done. What does that actually look like? In our implementations, we implement a spiking neural network. You can see an animation here. You got neurons and synapses. The neurons are flashing when they're firing, and they're creating spikes that are traveling throughout the network. Anytime you see color here, the neurons and synapses aren't doing anything. They're idle. That means less power. So with neuromorphic systems, they have really grown a lot over the last several years. We're up to 1 to 5 billion neuron systems. That's not quite human scale, but we're on track to get there. So there are these really exciting large-scale neuromorphic implementations that have the opportunity to change how we can do AI operations of the type that you are seeing when you are doing a Google query or using something like ChatGPT. Some of these large-scale systems look like what you would see in a data center or something that might sit on your future, desktop in your lab. However, in these future data centers, we could be incorporating these neuromorphic systems to decrease the energy cost of each of these individual queries so that you don't have to worry so much every time you're using ChatGPT and how much energy that's actually going to cost. Now, our research group is not just focused on these large-scale implementations, though. We are building neuromorphic hardware that is small-scale and meant to be targeted to more at-the-edge applications. We're pushing compute everywhere. You might have a smart washing machine, for all I know. We want to be able to push this sort of compute out to these edge applications as well. So we are building this sort of hardware here at the University of Tennessee. Now, we need different things when we go to the edge. We need real-time analysis. We need the ability to have energy efficiency, so you don't have to charge something like this every single day. We need resiliency. We need it to keep working, and we want them to be smart. We want to push AI out to these edge-based systems. Now, there are a lot of different sectors where neuromorphic could have an impact. In smart transportation, in pushing out to smart sensors to process data in real time and efficiently, in future drones and robotic systems, and in all of your various smart home activities, reducing the energy consumption there. We can also see neuromorphic systems in the future in health-based applications for real-time monitoring, in wearables, in future smart factories and smart manufacturing, and in future smart cities. So there's lots of opportunity here. Now, I wanted to give you a flavor for some of the projects we do with neuromorphic. So one of the places that we are using neuromorphic computing is to process data in real time as it's coming off of high-energy physics detectors. This data comes off super fast, so we want to be able to push the compute into the detectors like the one you see on the screen to be able to analyze the data in real time. We are also applying in a variety of other applications, including doing radiation detection at the edge for nuclear non-proliferation applications, deploying a neuromorphic system to look for radioactive sources and to be able to identify at things like border crossings. We are actively pursuing applications in smart transportation in a variety of places, including in improving engine efficiency. So we are working with transportation researchers in using neuromorphic systems to monitor engines in real time, including diesel engines and the engine you see here, which is a dual fuel ammonia diesel engine, to improve the fuel efficiency of those engines. And our group also does some fun stuff like have neuromorphic controlled 1/10 scale Formula 1 cars. Who wouldn't want to work on something like that? So one of the cool things associated with neuromorphic is that we are rethinking what the computer looks like from the top of the compute stack all the way down to the bottom. So we are not only reshaping what the architecture of the computer is, but we're actually thinking all the way down to the materials that we use to build these computers. And we here at the University of Tennessee are doing research across this whole stack. Now, this requires a huge amount of effort and interdisciplinary work. This is our research group and the students and faculty who have collaborated with us over the last decade in our neuromorphic computing research group. Phenomenal undergraduate and graduate students across computer science, computer engineering, electrical engineering, physics, mechanical engineering, neuroscience, and many others from those different applications that you saw. So hopefully, the next time that you do a Google search and you see that AI overview, or you have an application where you need intelligence at the edge, you'll think about neuromorphic computing. Thank you.